Thank you guys for having me out here today. And it's a special treat to be here because I really shouldn't be here. The person standing up here today should be Chris Pearson, who many of you know and get to work with on a daily basis. He's my collaborator from afar on this project, along with many others. And we've been working on some things in Hawaii for a little bit, and things matured enough that we were finally able to make some connections with data. And I'd like to share that with you today. What I'm going to say is the first observational link between black holes and dark energy. And I had the fortune of having, I guess, Adam go before me, so you guys have a taste of what dark energy is. Most of you, I think, have heard of black holes and may have some understandings or some thoughts about what they might be. And so let's begin. I'd like you to bear in mind two things during this talk. This is the famous predator handshake, of course, that the science that we do is an interplay between sort of, looking at things on paper, playing some games with math, what I'm going to call black hole models. Things like Kerr, things like Schwarzschild. These are not things that exist in space. These are not astrophysical phenomenon. They're models that we have that, with our limited abilities and the things that we've, figured out so far, we try to describe what's going on out there. Now, black holes are an interesting thing that they started on paper first, that we found them there. We thought we might be able to find these things in reality, and lo and behold, we did. And so now we're in the realm of astrophysical black holes, where we receive data from gravitational wave observatories. We receive data from the Event Horizon Telescope. We have data from AGN all over the place, surveys. And so we're really at this period now where we have this interplay between model and astrophysics. And so I'd like you to bear that in mind during this talk. Now, we're going to make a connection here between dark energy and black holes. And black holes are very small objects on astrophysical scales, maybe like 10 kilometers and growing from there. Whereas if we're talking about dark energy, we're talking about very, very large scales. For the galaxy surveys that Adam mentions, you're easily looking at many, many, many megaparsecs. And so how do we get oriented in this world? Well, our black holes exist, as Adam says, in a cosmology. So we have a growing thing. It starts from a Big Bang over here, and it's characterized in the theoretical discussion we're going to have by this thing called A, the scale factor. And that's the relative size of the universe relative to today. And today, A is 1. So as you go back in the past, the universe is getting smaller. We start in something called quantum fluctuations. We inflate things. The Big Bang gives off some light here. There's some dark ages. Things spark to life again after gravity starts pulling things together, heating things up. And then galaxies, stars, and now dark energy becomes apparent at the end. So black holes are objects that exist within a growing dynamic thing. Where's this whole picture come from? I'd like to draw your attention to this paper published in submitted, I guess, March 2nd, 1965. This is this famous Sakharov paper called The Initial Stage of an Expanding Universe and the Appearance of a Non-Uniform Distribution of Matter. And so Sakharov here was trying to figure out, how do the structures that we observe today with experiments like Euclid, where did they come from ultimately? And the suggestion here was that the initial inhomogeneities arise as a result of quantum fluctuations in some sort of really dense stuff, really far back in the past. And so that was the left-hand side of that diagram that I just showed you. And in the way of constructing this model, he has to use some really strange stuff at the time, and he footnotes it. And he says E.B. Gleaner, in a paper now in press, calls states with this property that he requires to get the initial inhomogeneities the way he wants, in connection with some technical sounding stuff, a mu vacuum. Now, I don't think anyone in this room has heard of the term mu vacuum. What is this mu vacuum? Let's go to Gleaner. This paper was submitted to the same journal 2 months earlier. Algebraic properties of the energy and momentum tensor and vacuum-like states of matter. Now that sounds almost like a contradiction. Matter is stuff that exists inside vacuum, is it not? So what is a vacuum-like state of matter? And I think that all of us throughout our careers have come across some sort of paper or some sort of result or a graph or something that just blew us out of the water, right? We're like, wow, this is the coolest thing I've ever seen. This paper to me was that. The physical interpretation of some algebraic structures of the energy momentum tensor allows us to suppose that there is a possible form of matter called the mu vacuum, which macroscopically possesses the properties of vacuum. And what he means by the properties of vacuum here is in a theoretical sense, that if I spin around, I can't tell that I've spun around. If I scoot, I can't tell that I've scooted. And if I change my velocity, I can't tell that I've changed my velocity either. And this material has very strange properties. It has negative pressure, and it doesn't have just small negative pressure or tensions. It has the maximally allowed tension that's still consistent with causality. I'd like to draw your attention to this paragraph on the right. This situation is not utterly unrealistic. An attempt to describe phenomenologically the structure of an elementary charged particle would lead to the conclusion that inside the particle, there must be negative pressure, which balances the electrostatic repulsion. This raises the thought that in an ultra-dense state of matter, with the baryons so compressed that the meson fields which provide the interaction between them cannot be produced, a continuous medium is formed, in which the conditions correspond to an attraction between material elements and are described phenomenologically by a negative pressure. For example, such a state might be reached in gravitational collapse. So you have here the origin paper of quantum fluctuations and this modern picture that we have of where we've come from. And this researcher, Sakharov, was talking with Gleaner, and the same material that's responsible for this inflationary situation is being invoked during stellar gravitational collapse. It would seem that a negative pressure should lead to an internal instability, and that if there are no volume forces of the type of the electrostatic repulsion, it would lead to a contraction without limit. This is not true, however. And he goes on to argue very cleverly with conservation of stress energy that the situation is stable. Now, it took some number of years. It took about 25 years until the solution was written down and Irina Gimnikova did it. The first vacuum non-singular black hole. It is a sphere that looks like Schwarzschild's black hole solution on the outside, the one everyone knows and loves, the non-spinning object. But on the inside, it has this de Sitter solution. So that's another way to say it is full of mu vacuum. It has no singularities anywhere. So our picture of black holes, this is actually a tattoo from this artist over here. Our picture of black holes, here we have here, where of course NASA is not doing well, falling in, never coming back out again, and being shredded in spaghetti is not the picture anymore for this scenario. For this object, we have something else. And so I'd like to show you, I don't know if this is visible, I hope it is. What I've drawn here is actually Schwarzschild's second solution. It's the constant density sphere. I think this was the 1917 solution. So this is going almost all the way back to the beginnings of general relativity and the first explorations that were done with it. And what I've done is I'm showing you the pressure here in color. So if we're orange colors, we're positive pressure. If we're green colors, we're in tension, we're negative pressure. Black is vacuum. This is the radius of the object. There's the object's radius measured in Schwarzschild units. And I'm showing you the pressure that's required to maintain a constant density stably. And so what's going to happen is I'm going to start squishing this thing. And I'm going to squish it more and more and more as I approach the Schwarzschild radius. And I'd like you to watch what happens. So as we go, I'm squishing it. You can see at the top. And the central pressure is going up, as you'd expect, going up, and then something weird will happen. Where'd that go? Dropped out the top because it's coming in the bottom. It's crystallizing from the inside out. There's a wave moving from the center of the object to the edge as we're crushing the edge in from the outside. When it's done, you have a region of negative pressure material, uniform, mu vacuum, and a very interesting boundary layer on the outside of the object, which turns out is not a horizon. This object is in causal contact with the rest of the universe. It's aware of what's going on. It can influence what's going on, and it can be influenced. So, surprise, there is a zoo of black hole models you've probably never heard of. These non-singular black hole solutions to general relativity with negative pressure that's equal to their energy density, as strong as you can get it, have been studied for more than half a century. Bardeen wrote a solution down 3 years after his Caltech thesis, didn't point out that it had this property, but it does. Dimnikova was the first person to really plow forward on this, and she's a real pioneer in this field. We have Visser down in Auckland, Francisco Lobo, plenty of other people. There have been quantum field theory motivated descriptions of these sorts of objects, condensed matter descriptions, that's Bob Laughlin over at Stanford. Mazur and Mottola were the ones that figured out that Schwarzschild's 1917 solution already had this physics in there, and no one had noticed it. That's the video I just showed you guys. There's assembly descriptions that show how this object can assemble, and a horizon never forms during the production of the object. And all of these solutions are very nice. They mimic or they're indistinguishable from Kerr or Schwarzschild on the outside. And that's because they share a property with Kerr and Schwarzschild, and that they are what's called asymptotically flat. They're static. They exist in emptiness alone. But that's not where we exist. We exist in a cosmology, in a dynamic, growing thing. And if they're indistinguishable from Kerr or Schwarzschild on the outside, how are we going to do science? We want to know what is the best description of nature that we can come up with. And so we want to leverage something about this situation to move forward. And so I'd like you to prepare for something wild. This paper, 2007, Faraoni and Jacques. What we're taught in school, and maybe you guys have encountered this, maybe not, maybe it's only cosmology school, but you're sort of taught that as the universe is cooling down and structures are forming, that at some point a region will decouple or disconnect from the cosmological growth, and then from that point forward it will go on its merry way and never be aware of the bigger universe in which it resides. And it turns out that that intuition is reasonable in many settings, but there's a couple of edge cases, quid pro quos. It is shown that this all or nothing behavior is limited. New exact solutions are presented which describe black holes perfectly co-moving within a generic Friedmann universe. A Friedmann universe is the sort of cosmology that we care about. So what's it look like? There's the solution. I won't bore you. Here's the conclusion. We have a local relativistic object with strong field. It's a black hole, which is perfectly co-moving at all times. In this case, the cosmic expansion wins over the local dynamics. So you've got a black hole that as the universe is growing, it's stretching this thing out. So models with realistic cosmological boundary conditions can exhibit new phenomenon. The first paper to point this out to my knowledge is Faraoni and Jacques. A black hole's radius and its mass are related. We knew that all the way back from Schwarzschild. So if you've got an object that's stretching as the universe expands, you might expect that its mass is changing too. This was investigated by Guariento in 2012. It turns out that you can have solutions that have dynamic mass and have a generic cosmology on the outside, but it wasn't clear how these two should be related to each other. Spoilers, this year, 2023, someone wrote down a solution that has this dynamic behavior and everything. So, but that's a little spoiler. So in the state before 2023, how do we make this connection? How do we look for Gleaner's objects? And so we're going to leverage something called cosmological coupling. And so this was the work that we did theoretically in Hawaii. We dug into not looking at the problem from the small scale and trying to go outward. We started from the largest scales and we went inward. And we exploited some Fourier techniques and some fancy math to extract a prediction from GR that if a species of compact objects contributes non-zero pressures to Einstein's equations, then the individual masses will observably shift, analogous to the photon redshift. So for a long time, we've known that light, very distant to us, shifts as the universe expands. And so the older something is, the redder something is. Now, light is a weird thing, though, in many other ways. And so we've had to just deal with this, and we've accepted it as an observational fact, and light is weird. Well, turns out other things with pressure too can be weird. Light has pressure 1/3, by the way, in relativistic units, positive 1/3. So we're going to say the masses can shift to this power of the scale factor. So AI is the scale factor at the time of coupling. Remember, A gives the linear scale of the universe. Mi is the mass at which the body becomes coupled. So when A is equal to AI, that's 1. So we recover this. And K is the strength of the coupling. Now I've written out K explicitly here to show how it's related to the pressure. It's -3 times the pressure divided by the energy density times c squared. That c squared factor is quite large. So you need really strong pressures to be able to ever see this sort of effect. There's a little candy noise. Sorry, I'm sensitive to noises. So if you compute this for something like the sun, or the core of the sun, this is 10 to the -6. The mass change dominated by stellar mass wind losses. You won't be able to see it. So if you want to hunt for this effect, if you want to be able to ask the question, are black holes cosmologically coupled? We need a population of relativistic objects where the pressure is approaching the energy densities, and we need the ability to observe them for a long time. So we need this ratio to be much larger than 1. Now, what I've done here is here it's expressed in the sort of linear scale of the universe. Here I've flipped it into the observational quantity, something that's called redshift. And so redshift is conveniently the reciprocal, and then you just add 1. So we flip that up. As Z gets large, we're going back in the past. Some points of reference, the Big Bang is around Z 1095, the light that we see from it. First stars happened around maybe Z 25. So if you want more information, by the way, that establishes this stuff, you can bang these QR codes. So what did we do? We looked at galaxies, and we looked at particular galaxies. We didn't look at spirals. We looked at these very old, nice, uniform galaxies. These are called ellipticals, and we looked at very massive ellipticals. The idea was that a galaxy is a very complicated thing, but it has a black hole in it, and it has a black hole that we can measure, and there's data that has measured this already. So if we carefully select these objects to try to rule out any other sort of way the black hole could be growing, then maybe we could try to measure this effect. And so we looked at massive ellipticals. We looked at them with star formation rates that were extremely low compared to other objects at that epoch, very gas poor, so there's no way to build up star material, no way to feed that central black hole more. Very, very nicely uniform, so there's no recent evidence for a merger event. And we looked for the very most massive galaxies, lots of stars, probably the end stages of their evolution. And so these are the samples we put together. This is a Cosmos sample from redshift 1.61. It's a median. That's around 9 billion years ago. And it's a small sample, but you can see this little diagonal trend. The y-axis here is the mass of the central black hole in solar masses log. Down here is the stellar masses in solar masses log. And you can see that's got this diagonal trend that I mentioned before. The reason you see a diagonal is that typically the way galaxies assemble, the processes that build up stars also build up the central black hole. If you have gas, some of that gas will end up in stars. Some of that gas will end up on the black hole. If you have a merger, well, you've just combined all your stars, and the black holes will probably find each other, the central ones, and so those go up too. And so you tend to cruise along a diagonal. And you can see that more clearly here in this WISE sample, which we pull from about redshift 0.85. That's about 7 billion years ago. And it says the same basic slope. We have many more little objects that look like antibodies. So what are we doing now? Let's compare this to these same objects at the present day. And there's the local ellipticals. And you can see again this same type of diagonal slope, but it looks like there's a lot of travel going in the black hole direction and maybe not so much travel in the star direction. And just to sort of hammer that in a bit, here's the median values for these populations. If you go from the Cosmos population up to ellipticals, that's like 20. This is because this is DEX over here. So did we find cosmological coupling with this figure? No, we did not. This figure is a swindle because we aggregated data from how many different experiments that measured black hole masses in how many different ways, measured stellar masses in different ways, they're pointing at different places in the sky. There were so many observational biases, selection effects. Like, we took us a year to sort all of this out to get any sort of thing that we had any confidence in. But we worked very hard, and we put together a really large team to make sure that we were crossing our T's and dotting our I's the best that we could. And this is what we came up with. So in this study, we've worked with a bias model, and we've incorporated the uncertainties on every one of those little antibody points in the previous slide. And this is what we found. So I've color matched this to the previous slide. So the Cosmos sample is still orange. The Y sample is still blue. There's no red sample here because instead I've drawn a green sample, which is the same types of objects measured with black hole masses measured by a different technique, so that we can try to check, make sure that we're not too biased. And so this should line up with 0, and it mostly does. And what you're seeing here are offsets. So the idea for this was like, okay, what do we need to do in this diagram here to cause these other older populations to line up with the locals in the sense that they're statistically indistinguishable? And so we're going to monolithically shift the old populations up and down and left and right to try to align them with the locals. These are those offsets that were required to do that once we had the bias corrections and the uncertainties folded in. In the stellar direction, we see that they're consistent with 0. But in the black hole direction, we see that they're very not consistent with 0, except for this one, which should be. These got larger, these shifts. So when you properly account for the biases, the problem gets larger. And so, is this a signature of cosmological coupling? Well, here's what we did for that. Because cosmological coupling depends on that ratio of scale factor over the initial scale factor when the object was formed, we have to go through now and look at each galaxy that's measured and when it was measured, and we have to shift each individual object by its own unique amount, depending on when that data came to us, when the object came to us, the data. And so now we do a different experiment where we don't monolithically move the populations around. We move each individual object up and down in the black hole direction, and we ask, what value of that exponent, what value of k causes the data to best align with the local population? Now, we've even folded in a different data set here from Sloan, and we've split this data into 2 different redshift bins. This is measured with a hydrogen beta line. This is measured with a magnesium 2 line. And we did this again to try to make sure that we had a handle on various systematics. Here's that Cosmos sample. You can see that they cluster around a k of 3. In fact, if you lump them all together, we find that k equals 0, or no coupling, can be excluded at pretty high confidence, 3.9 sigma. And if you extract a k measurement from this, you find that k is 3.11 plus or minus 1.2 at 90% confidence. So k equals 3 is a sort of magical value because it's the largest that it could be, and it leads to a very interesting consequence. If each black hole satisfies coupling with k of 3, then the mass of a black hole, once it's formed, grows with the volume of the universe. But black holes exist in a cosmology. And so as the cosmology expands, the number density of black holes dilutes. And so that goes down as the cube. So the energy density of black holes is constant. A cosmological constant, the most boring thing you can study. So, cosmological conservation of stress energy, this is pulled directly from Einstein. This has to be 0. This is not 0 because this describes the growth of the universe. So that means this has to be 0. And so the pressure from the black holes is equal to the negative of the energy density from the black holes. And I've left off the c squared, but it's sitting there. And so that means black holes in aggregate contribute as a dark energy species, which is what you would have expected from Irina's solutions. Actually, Irina's solution can't do it because it has a horizon. But all the other solutions that she's worked on and everybody else that don't have horizons can contribute in this way. So Can we put all this together? Can we eliminate the need for a cosmological constant that is not motivated and actually have an astrophysical source for this thing? So we know that the energy, this mu vacuum, inside these non-singular and horizon-free black hole models can couple. Let's assume that accretion is subdominant for the moment. And so the only way that these things are growing is through this coupling effect. And so they're going to mimic a constant. Can we get all of the constant? And so let's assume that black holes are the only source of cosmological constant. So there's no like Einstein type contribution, and there's no sort of I'm getting ahead of myself here. There's no Einstein contribution. There's no light scalar fields. There's nothing fancy. I know you're laughing at me. I am. And let's assume the stellar gravitational collapse is the only source of black holes. And so there's been discussions of things like primordial black holes or direct collapse black holes. And so we're not going to think about those at the moment. We're just going to ask the question, can stellar gravitational collapse black holes do it? And so what do we find? So there's a lot to unpack in this figure. But the general idea is on the y-axis, you're looking at your star formation rate density. How many suns per co-moving megaparsec cubed per year? On the horizontal axes, you're looking at age, and you're getting older as you go to the right. So this is this redshift that I mentioned before. This is look back time in gigayears. Anything that's sitting in the green, if I draw a monotonically decreasing line, I'm choosing some sort of star formation rate because I'm drawing a line in this plane. I can pick that rate, and there will be a distribution of stellar masses at birth and some prescription for how much mass is being accreted onto black holes that come from those stars that will give you the observed amount of dark energy today. And so what I'm indicating here with the data points is just to get a handle on sort of what things have to bound what has been proposed. And so up here in the sort of a little unreasonably high territory is this Rowan-Robinson infrared measurement of the star formation rate. So infrared measurements are an upper bound on the star formation rate because you get IR from obscured formation. Over here, this is stuff from James Webb Early Science release, these Harakonic and these Bowen's points. These are from ultraviolet dropouts. Those give you the lower bound because they can underestimate what's going on. And so it looks like we have some nice territory in here where we can make this scenario work. This dashed line, by the way, is sort of a fiducial star formation rate model that's been sort of in the literature for a while, and it's reliable. So on this graph, we have ground-based stuff. This is an ALMA point. And then we have James Webb stuff. To really start filling this in, James Webb is going to be a wonderful, wonderful thing. And then 21 centimeter experiments, as they're coming up, will really start to fill in this territory over here. So, in summary, known black hole models suggest, and Einstein's equations allow, black holes to cosmologically couple and gain mass to the scale factor raised to some power. The anomalous supermassive black hole growth that we've found in elliptical galaxies is consistent with coupling, and we exclude k = 0 with this population at high confidence. The measured value of coupling that we find is 3, implies that black holes contribute as a cosmological constant, like a dark energy species. Stellar collapse remnant black holes can give you the right value, given the measured star formation rate and current literature best estimates for what's the distribution of stellar masses at birth and accretion. And if your system has a black hole in it, and you can watch it for a long time, you're going to see signatures of this. There's numerous ways to confirm or refute this measurement. And so please, if you have any ideas on ways to confront this observation we've got and this model we've put together with data, please get a hold of me. And so I ask next time you look at one of these objects, don't necessarily judge a book by its cover. Thank you.
Okay, I think we've got time for one quick question before we take a short break. Any questions? One online? Excellent. So what does this model of black holes tell us about the black hole information paradox?
So the black hole information paradox, at least my understanding of it, and I'm not an expert in this aspect of local solutions, is something that comes about because of a horizon. So you have this sort of one-way layer where like things go in and then they somehow get reprocessed into some surface entropy of the black hole. And like, how do I get the information back out again? Because now it's just thermal. And so if you don't have a horizon around anymore, because you're in causal contact, because you're coupled, then I don't think you have an information paradox anymore.
Thank you. Okay, so thank you very much to all the speakers for this session.